The massive scale of the modern data ecosystem was ultimately born out of inevitable mechanical failure, not preference. For decades, traditional relational database management systems, or RDBMS, held everything. But as this animation shows, rigid, monolithic SQL tables physically crack when hit with the modern trio: massive volume, high-speed data velocity, and irregular data variety. Historically, the solution to more data was vertical scaling, buying a bigger, more powerful server. But when a dataset crosses into the petabyte range, a single machine simply cannot hold it, let alone process it. The answer to this bottleneck is a complete architectural pivot. Instead of centralizing power, the system decouples storage from computation, spreading the workload across a distributed network of independent machines. To survive the sheer scale of modern data, organizations have to abandon singular monolithic structures and build fault-tolerant modular platforms from the ground up. Before constructing that new architecture, we have to define exactly what is arriving at the ingestion gates. The classical input is structured data. These are highly organized entries from traditional transaction processing systems: names, dates, and financial figures that fit neatly into predictable rows and columns. Looking at this textbook classification, structured data breaks down further by measurement scales. Nominal scale data represents flat categories or labels without any inherent order, like product types. Ordinal scale data represents categories with a natural ranking, such as survey responses, but the exact mathematical distance between those ranks is unknown. Moving down the page, we find interval and ratio scales. Interval scale data provides consistent, meaningful distances between numerical values, like temperature, but lacks a true zero. Finally, ratio scale data provides an interpretable distance and a true zero, allowing for precise arithmetic, like measuring income. But those highly structured inputs now make up only a fraction of enterprise data. The vast majority of new inputs arrive as unstructured data: video logs, raw audio, and plain text emails. In between sits semi-structured data, formats like XML, JSON, and HTML, which carry tags and markers but lack a rigid tabular framework. Because modern data arrives without a uniform structure, our ingestion and storage layers must be highly flexible. We can no longer force incoming data to conform to a strict schema the moment it is written. This requires a total reconstruction of the ingestion pipeline, the first layer of our new architecture, responsible for moving raw data from disparate external sources into our system. The legacy method is ETL: extract, transform, load. Data is pulled, pushed through middleware to reformat, then loaded into the warehouse. But this transformation step creates a massive bottleneck, halting high-velocity streams. The modern solution is ELT: extract, load, transform. Raw data bypasses middleware, loading directly into storage. This reversal works today because modern platforms provide massively scalable, highly cost-effective storage capable of holding huge amounts of unformatted data. By transforming data only on demand, we prevent critical data loss during high-speed ingestion and preserve the original fidelity of the data for future analytical models. Once that raw ELT pipeline data clears the ingestion gate, it drops into the foundational repository layer, where it physically sits across racks of commodity hardware. This is the Hadoop Distributed File System, or HDFS. The top name node acts as the master server, managing the namespace and regulating client access without holding actual files. Below, the slave data nodes physically store the data blocks and execute all read and write requests. Inside those data nodes, HDFS chops the incoming files into minimum units, typically 64 megabyte blocks. To protect against hardware failure, the name node automatically copies these blocks and distributed the replicas across different nodes in the cluster. By abstracting the physical complexity of thousands of independent drives, HDFS creates a single, highly available logical file system that scales horizontally without limits. While HDFS is excellent at holding raw files, querying nested relationships within that data requires a database system layered directly on top of the storage. This text details the NoSQL paradigm, using MongoDB as a primary example. Unlike rigid SQL structures, MongoDB utilizes a schema-less design, meaning individual records inside the database do not have to mirror each other. In this model, traditional databases and tables are replaced by flexible collections, and strict rows are replaced by individual documents.
As illustrated here, MongoDB physically stores these entries using BSON. A nested plain text JSON document is compiled down into a highly efficient binary representation. This binary format allows the system to store complex, nested arrays of information inside a single document. It eliminates the need to write and execute processor-heavy SQL joins across multiple tables.
By embracing a schema-on-read philosophy and efficient binary models, NoSQL databases dramatically accelerate the querying and fetching of highly varied datasets. With petabytes of data securely stored and organized, we hit the compute layer. Instead of trying to move massive datasets to a central processor, we push the processing instructions down to where the data physically sits. This relies on MapReduce. A massive dataset splits into discrete blocks, distributed across multiple computing nodes. In the map phase, nodes perform parallel processing, converting raw information into color-coded key-value pairs. In the reduce phase, pairs are shuffled and aggregated into a unified output. Initially, in Hadoop 1.0, this system had a fatal flaw. The MapReduce engine was tightly coupled to a single resource manager, creating a massive processing bottleneck. Hadoop 2.0 solved this by introducing Yarn, which stands for Yet Another Resource Negotiator. As outlined in this text, Yarn acts as a large-scale distributed operating system. Yarn decouples the processing engine from hardware management. The global resource manager strictly handles cluster usage, while localized node managers launch and monitor individual application containers on the slave machines. By separating the processing engine from hardware management, Yarn allows multiple data processing frameworks to run simultaneously on a single cluster, establishing a multi-tenant environment for large-scale distributed processing. Finally, we reach the presentation layer, how this massive architectural stack actually interfaces with business analysts and end users. A marketing team cannot efficiently run daily queries directly against a petabyte-scale data warehouse. It is too slow, too complex, and consumes too much compute power. The solution is the data mart. As detailed here, a data mart is a specialized, smaller-scale subset of the main data warehouse, specifically tailored for a single functional area or department. The ideal structure is the dependent data mart. It extracts its data directly from the central warehouse, ensuring that while the marketing team gets a fast, focused slice of the data, the entire enterprise maintains a single, consistent source of truth. Data marts operate as the highly optimized storefronts of the big data platform. They deliver rapid, curated insights while shielding end users from the vast mechanical complexity of the underlying cluster. Zooming out, we can trace the complete architecture from raw ingestion to operational insight. High-velocity data is captured by ELT pipelines at the ingestion layer, dropping into a repository secured by HDFS and structured by NoSQL. Above this, the compute layer uses Yarn and MapReduce for localized processing. Finally, analytics filter into specialized data labs for end users. The functional definition of big data lies in this requisite architectural ecosystem. This modular, infinitely scalable platform provides the infrastructure necessary to transform high-velocity, unstructured data into actionable operational intelligence. Finally, we reach the presentation layer, how this massive architectural stack actually interfaces with business analysts and end users. A marketing team cannot efficiently run daily queries directly against a petabyte-scale data warehouse. It is too slow, too complex, and consumes too much compute power. The solution is the data mart. As detailed here, a data mart is a specialized, smaller-scale subset of the main data warehouse, specifically tailored for a single functional area or department. The ideal structure is the dependent data mart. It extracts its data directly from the central warehouse, ensuring that while the marketing team gets a fast, focused slice of the data, the entire enterprise maintains a single, consistent source of truth. Data marts operate as the highly optimized storefronts of the big data platform. They deliver rapid, curated insights to the team, while shielding end users from the vast mechanical complexity of the underlying cluster. Zooming out, we can trace the complete architecture, from raw ingestion to operational insight. It begins at the ingestion layer. High-velocity data in widely varied formats is captured by ELT pipelines, completely bypassing traditional transformation bottlenecks. That raw data drops into the repository layer, secured across fault-tolerant HDFS racks and structured by flexible NoSQL databases like MongoDB. Overlaid on this storage is the compute layer. Yarn manages the cluster resources, while MapReduce executes parallel processing directly on the distributed data blocks. The resulting analytics are pushed to the serving layer, filtering into distinct data marts that deliver specific intelligence to end users. The functional definition of big data lies in this requisite architectural ecosystem. This modular, infinitely scalable platform provides the infrastructure necessary to transform high-velocity, unstructured data into actionable operational intelligence.